This podcast was created by Dr. Alyssa R. Jones for PSYC 5300 graduate level behavioral statistics using Notebook LM. The system was given specific parameters and restricted to content drawn from the assigned Crump Lab texts, answering questions with data and reproducible statistics for psychologists with R. The narration is produced using AI-generated voices. These voices do not represent recordings of Dr. Jones or the authors of the assigned materials. Although the podcast was generated from the designated course text, AI-produced summaries, explanations, and narration may still contain errors, omissions, or oversimplifications. Students should use each episode as a learning supplement and consult the assigned readings, course materials, and instructor guidance when clarification is needed.
You look at the final output of your statistical software, and there is a score of 75 on a major psychological assessment you've been analyzing.
Right. And for most of us, deeply conditioned by decades of standard educational grading, that number triggers a pretty immediate visceral reaction.
Oh, absolutely. It feels thoroughly mediocre. I mean, we've been trained to anchor a 75 to this rigid 100-point scale where 100 is absolute perfection and 50 is just, catastrophic failure.
Yeah.
So 75 is just sitting there in the muddy middle. You survived, but you certainly didn't uncover anything groundbreaking, right?
But that reaction is a perfect example of how our intuition about numbers often betrays us when we actually step into the realm of true data analysis. We bring these preconceived arbitrary scales into our research.
We really do.
But what if we completely detach that 75 from the grade school framework? Once we actually translate the data, once we look at the underlying distribution of the population, that seemingly mediocre 75 might reveal that your subject didn't just do okay.
Right.
They might have exhibited a trait or a performance level that outpaces almost every single person in the room.
Which fundamentally changes the entire narrative of your research finding.
Completely.
Welcome back to the Deep Dive, everyone. And today we are speaking directly to you, the psychology graduate students who are continuing this rather intense methodological journey with us.
That's right.
Last week, we spent our time analyzing discrete distributions. We operated in what we're calling the chunky world of probability, dealing with very distinct countable events.
Right. We were looking at things like our theoretical binomial distribution experiments, rolling those imaginary sets of 20 dice with skulls on the faces, counting the exact integer number of skulls that turned up.
Or analyzing categorical choices. We used the admittedly simplistic example of choosing between exactly 5 pairs of pants in a wardrobe.
Yeah, you are either wearing the blue jeans or you aren't.
Exactly. There is no reality where you select like 1.57 pairs of pants.
I mean, unless things have gone horribly wrong in your morning routine.
Right. But that framework is incredibly rigorous and useful for specific types of data like counting the number of times a rat presses a lever or tallying yes or no responses on a survey.
Yeah, discrete variables.
But as you plunge deeper into psychological research, you hit a wall. Human behavior, underlying cognition, nuanced emotional states, they completely defy those neat, chunky, discrete boxes.
They do. The transition you have to make as a researcher is moving from counting distinct events to measuring theoretical constructs. And that requires a completely different mathematical language.
Which gives us our mission for this deep dive. We are going to build the bridge from that countable world of discrete events into the smooth, infinite, and continuous world of the normal distribution.
Yes.
We are going to pull apart the mechanics of the Gaussian curve, the ubiquitous bell curve, to understand exactly why it dominates psychological data.
We'll look at the central mechanism behind this too, the central limit theorem.
Right. And finally, we will explore how standardizing data using z-scores provides a translation layer that lets you compare wildly disparate metrics. We are decoding how to definitively compare apples to oranges without getting laughed out of peer review.
Exactly. But to make that leap, we first have to fundamentally deconstruct how we think about probability. Let's briefly hold on to the discrete model from last week just to contrast it.
Okay.
When you plotted the outcome of rolling those 20 skull dice, you created a probability mass function, You constructed a bar chart, basically a histogram.
Right, you have a solid, distinct bar for rolling exactly 0 skulls. Next to it, a bar for 1 skull, then 2, all the way up to 20.
Yeah.
And we saw that the probability of rolling exactly 4 skulls out of the 20 is a very specific calculable number. It was roughly 20%.
But look at the visual representation of that data.
Yeah.
The horizontal spaces between those bars are entirely empty voids. The mathematical function simply does not exist at 3.9 skulls or 4.1 skulls.
Right, you can't roll a 0.9 of a skull.
The universe of that data set only allows for whole integers. Now, sweep that off the table and consider a truly continuous variable. Consider measuring the ambient temperature of your laboratory.
Okay, so I look at the digital thermometer on the wall, and it reads 23 degrees Celsius.
But as a scientist, you know the room is not exactly 23 degrees.
Of course not. That's just the limitation of the wall sensor. I mean, if I bring in a highly calibrated research-grade thermal probe, it might read 23.15 degrees.
Right. And if we move to a theoretical standard of infinite precision,
And then it might be 23.1409982 and just continuing infinitely. The precision has no boundary.
exactly, it is a genuinely continuous quantity, much like time, physical distance, or, as we often conceptualize them, underlying psychological traits.
Right.
Because the data is continuous down to an infinite decimal, we can no longer draw our probability as a series of chunky bars. If we tried, we would need an infinite number of infinitely thin bars.
Which would just look like a solid block anyway.
Exactly. Instead, the mathematics smooths out into a continuous curve. This brings us to the normal distribution. You no longer have a probability mass function, you have a probability density function.
And this normal curve is defined by just 2 parameters, which is actually quite elegant. First, you have the mean, which is the center point of the distribution.
Right.
If you alter the mean, you don't change the actual shape of the bell at all. You merely slide the entire curve left or right along the horizontal x-axis.
Yeah, you're just moving it. The second parameter is the standard deviation, which dictates the spread or the variance of the data.
Okay.
A very small standard deviation means your data is tightly clustered, resulting in a tall, narrow spike of a bell curve.
Like a needle.
Exactly. A large standard deviation stretches that curve out, making it wide, flat, and highly dispersed.
But here is the massive conceptual hurdle that trips up almost everyone, and it certainly tripped me up when I first stared at these graphs in a graduate statistics seminar. Yeah. When you look at the axis of a continuous normal distribution, the label is not probability, it is probability density.
This is a vital distinction. In the discrete world, the height of the bar on the axis gives you the exact probability of that event occurring.
Great.
But in the continuous world, the height of the curve does not give you a direct probability percentage.
Which is so confusing at first. Our source material highlights an incredibly counterintuitive reality of continuous probability. If I ask my statistical software to calculate the probability that the temperature in the room is exactly 23 degrees, and I mean exactly 23, with an infinite string of zeros trailing behind it, the software will tell me the probability is 0.
Right, it is functionally 0.
The analogy from the text is just brilliant. It asks you to imagine throwing a dart at a dartboard. But the target you were trying to hit is a single, infinitely small mathematical point.
Yes, it has no width, no height, no physical dimension whatsoever.
Exactly. It doesn't matter if you are the greatest dart player in human history. The odds of the absolute center of your dart hitting that infinitely dimensionless point are 0. You will always be slightly off, even if it's by the width of a single atom.
Applying that to our temperature example, out of the infinite possible temperatures, the room could theoretically be like 23.0000000 or 22.9999999. The chance of it landing exactly on 23.0 repeating to infinity is literally 0.
But, and this is where I got stuck, if the probability of any exact value is 0, how do we ever calculate anything? When I first encountered this, I thought the entire system of statistics was fundamentally broken.
A lot of students think that.
Right. Because we are trying to measure probabilities, but the math tells us every specific outcome is impossible.
Well, the system isn't broken, but your line of questioning has to evolve. You have to stop asking for the probability of a single exact point. Instead, you must ask for the probability that a value falls within a specific range. We stop asking, what is the chance it is exactly 23? And we start asking, what is the chance the temperature falls between 22.9 and 23.1?
Oh, I see. So geometrically, we are no longer looking at the height of a single vertical line. We are calculating the area under the curve between those two boundaries.
Precisely. The probability density on the axis tells you the relative concentration of the data. Higher density means values in that neighborhood are generally more likely.
Right, that's the fat part of the bell.
Exactly. But to extract a true workable probability, a percentage chance, you have to integrate over a range. You have to measure the area.
So if we pull this out of abstract temperature metrics and drop it right onto the lap of a psychology grad student designing a study, the implications are massive. Think about measuring a construct like general intelligence or trait neuroticism.
Right, because true psychological constructs are theorized to be inherently continuous.
Yes. We never measure a subject's true Platonic ideal of intelligence down to the infinite decimal. We capture a messy snapshot. When someone scores a 115 on a cognitive assessment, their underlying theoretical cognitive capacity isn't exactly 115.00000.
No, it's not.
That score simply places them within a specific density, a probabilistic range of where their true trait likely resides.
And because we are mandated to deal in these ranges, and because the total area under any probability density curve must always equal exactly 1 representing 100% of all possible outcomes, we require a universal system to carve up and measure those ranges.
We need a map.
Exactly. We need a standardized cartography for the bell curve.
But measuring the area under a curve using raw integral calculus every time we run a participant through a study is wildly impractical.
Completely impractical.
Yeah, a working researcher needs a shorthand. We need to instantly know if a data point is an expected variation or a bizarre anomaly. That necessity gave rise to the empirical rule, the gold standard heuristic for navigating the Gaussian distribution.
The empirical rule allows you to instantly map the territory of any normal distribution, regardless of its specific parameters.
Okay.
It doesn't matter if your mean is 0 or a billion. It doesn't matter if your curve looks like a needle or a gentle hill. If the data is normally distributed, the geometry of the curve dictates a very strict set of proportions.
This is the famous 68-95-99.7 rule. Our source material is appropriately rigorous here, utilizing the more exact figures of 68.3%, 95.4%, and 99.7%.
Right.
But I want to push on the why before we get to the what. Why these specific, seemingly arbitrary percentages? Like, why does one standard deviation capture exactly 68.3% of the area?
That is a phenomenal question that rarely gets explained in introductory
I
seminars.
usually just tell you to memorize it.
Right, just memorize the numbers.
Yeah.
But it actually comes down to the mathematical inflection points of the bell curve.
Inflection point.
Yeah. If you trace the shape of a normal distribution starting from the absolute peak in the center and begin sliding down the right side, the curve is initially convex. It is shaped like a dome, accelerating downward.
Okay, I can picture that.
But at a very specific point along that descent, the curvature changes. It stops accelerating downward and begins to flare outward, becoming concave as it stretches into the long tail.
Oh, the slope stops getting steeper and starts leveling off.
Exactly. That exact point of transition, the mathematical inflection point, is located perfectly at one standard deviation away from the mean.
Wait, really?
Yes. The underlying calculus of the Gaussian equation intrinsically places 68.3% of the total area between the negative inflection point and the positive inflection point. The math organically creates these boundaries.
Wow, that makes the standard deviation so much more than just an arbitrary measuring stick. It's physically tied to the shape of the curve itself.
It is.
Let's map this onto a practical scenario so it sticks for the listeners. We'll use standardized IQ tests because they are the classic, albeit somewhat engineered example of this geometry in action. They're specifically calibrated to have a population mean of 100 and a standard deviation of 15.
Okay, so applying the first step of the empirical rule, we look at the range between -1 standard deviation and +1 standard deviation.
Right.
That means we subtract 15 from the mean of 100 to get 85, and we add 15 to get 115. The rule dictates that 68.3% of the total area under the curve falls within this specific range.
Meaning that over 2/3 of the entire human population will score somewhere between 85 and 115. That massive 2/3 majority forms the giant, dense hump of the bell shape.
Yeah, that's the bulk of everyone. Moving out to the second step, the rule states that 95.4% of the data falls within ±2 standard deviations.
So 2 standard deviations is 30 points.
Yeah.
Look at the range from 70 to 130.
Right.
Fully 95.4% of the population exists within those boundaries.
And finally, 3 standard deviations, which is a 45-point spread in either direction. 99.7% of the data, almost the entirety of the distribution, falls between 55 and 145.
So the power of this for a graduate student parsing through raw dataset outputs is just pure intuition, right? If you are reviewing the descriptive statistics of a new sample and you see a participant scored a 135 on this cognitive assessment, you don't need a calculator to understand what you're looking at.
Not at all. You immediately know that 1 into 30 is the two standard deviation boundary. A score of a 135 pushes them well beyond that 95.4% bulk of the population.
They are out in the extreme upper tail. Without running a single formal statistical test, your internal compass flags this as a statistically rare observation.
Right. Furthermore, clinical and diagnostic criteria rely heavily on these exact boundaries.
Oh, true.
In many jurisdictions, the threshold for certain cognitive interventions or diagnoses isn't based on a qualitative assessment, but rigidly on these standard deviation cutoffs. Scoring 2 standard deviations below the mean is often the strict legal boundary for defining intellectual disability in a research context.
So the empirical rule is quite literally written into diagnostic manuals.
It is.
Now, the elegance of the math is undeniably beautiful, but as a researcher dealing with the actual messy realities of human beings, I have a major pushback here.
Let's hear it.
The IQ example is almost too perfect. Psychometricians spend years deliberately engineering test items, dropping outliers, and basically forcing the data into that perfect normal distribution with a mean of 100 and an SD of 15. It's artificial.
Yeah, they do smooth it out.
But when we measure genuine human behaviors in the lab, say, reaction times to a startling image, or the amount of cortisol in saliva, or the degree of social conformity in a group setting, that data is chaotic.
Highly chaotic.
It is often wildly skewed, it has heavy tails, so why on earth should we assume that the organic, unpredictable human behaviors we study will magically conform to this pristine 68, 95, 99.7 geometry?
That skepticism is exactly the hallmark of a good scientist.
Yeah.
You're absolutely correct that we should never blindly assume raw human behavior follows a perfect bell curve. Reaction times, for instance, are notoriously skewed.
Yeah.
You can't react in less than 0 milliseconds, so there is a hard boundary on the left. But a participant could theoretically take an infinitely long time to react, creating a massive long tail stretching out to the right.
Exactly. The raw data is a mess.
But your observation leads us directly to the bedrock of inferential statistics. It leads us to a theorem that explains why, despite the chaotic messiness of raw data, the normal distribution continually emerges as the defining architecture of our analyses.
We are talking about the central limit theorem, the CLT.
Yes. It is the single most important concept to grasp if you want to understand why your statistical software does what it does. The central limit theorem is the mechanism that bridges the gap between chaos and predictability.
I remember reading the formal definition of the CLT in my first year of grad school, and it honestly felt like mathematical sleight of hand. Like it felt like a trick to make the math easier for researchers.
It feels mystical, I agree, but it is deeply grounded in the physics of aggregation. Let's state the theorem formally. The central limit theorem dictates that if you extract multiple independent samples from a population, calculate the mean of each of those individual samples, and then plot a new distribution composed purely of those sample means, that sampling distribution of the means will approximate a normal Gaussian bell curve.
And the absolute kicker, the part that feels like magic, is that this happens completely regardless of the shape of the original population's distribution.
Yes. The underlying population could be shaped like a uniform block. It could be severely skewed to the right, like your reaction time example. It could be bimodal, with 2 massive peaks and nothing in the middle.
Right.
It does not matter. If your sample size is sufficiently large, the distribution of the means of those samples will inevitably organize itself into a normal distribution.
Okay, we have to visualize the mechanics of this for the listener because it's just not intuitive until you see it happen. The source material outlines some phenomenal, concrete simulations to prove this. Let's start with a population that is emphatically, aggressively not normal.
Let's do it.
Let's use a uniform distribution.
Imagine a massive, opaque container filled with millions of plastic tokens. Each token has a single number printed on it, ranging from 1 to 10. Because it is a perfectly uniform distribution, the container holds exactly the same number of 1s as it does 2s, 3s, 7s, and 10s.
Right. If we graphed the probability of pulling any single specific number from that container, the graph would just be a flat horizontal line, a rectangle.
Yeah.
Every single number from 1 to 10 has a perfectly equal 10% chance of being drawn. The true population mean of all these numbers is 5.5, but there is no bell shape around that mean.
Not at all. Now we execute the sampling procedure. We reach into the container and randomly extract a sample of 20 tokens. We record those 20 values. We calculate the average of that specific handful, and we get our first sample mean.
Let's say by pure random chance, our first handful had a slight surplus of 8s and 9s, so the average of those 20 tokens is 6.2. We plot that single data point, 6.2, on a brand new, empty graph.
Right. Then we return the tokens to the container, mix it thoroughly, and draw a second sample of 20. We calculate the new mean.
Maybe this handful is heavy on the 1s and 2s, yielding a sample mean of 4.1. We plot that on our new graph.
We repeat this exhaustive process 10,000 times. We have now generated 10,000 separate sample means. When we look at the histogram of those 10,000 averages, what shape emerges?
The flat rectangular block is entirely gone. The new graph displays a pristine, symmetrical bell curve with the massive peak centered dead on the true population mean of 5.5.
It's incredible. The raw data was a flat block, but the average is synthesized into a normal distribution.
When you really sit with the logic, it loses the magical feeling and becomes kind of inevitable. Think about what it would take to get a sample mean of 10. You'd have to reach into the container and randomly pull out 20 10s in a row.
Yeah, the probability of that happening is staggeringly, astronomically small.
Exactly. The same applies to getting a sample mean of 1. You would need 20 consecutive 1s.
But to get a sample mean around 5.5, you don't need any special sequence. You just need a typical, messy, random assortment of high numbers and low numbers that naturally cancel each other out.
Right. And because there are millions of combinations that average out to the middle, and only one combination that averages out to the extreme edges, the distribution naturally bulges in the center and tapers off at the sides.
The extremes neutralize one another during the act of averaging. The source material pushes this even further to demonstrate the robustness of the theorem. It asks us to consider an exponential distribution.
Oh, this is a shape that grad students fear. An exponential distribution looks like a steep ski slope. Small values are overwhelmingly common, creating a massive peak on the far left of the graph, and large values are exceedingly rare, creating a long, thin tail stretching out to the right.
Yeah, it is as far from a symmetrical bell curve as you can get. Yet, if you execute the exact same procedure drawing samples of 20 from that ski slope, calculating their means, and plotting the distribution of those means,
You get a bell curve.
Yeah.
The CLT forces the exponential chaos into a normal distribution.
Furthermore, the theorem dictates that as you increase the size of your individual samples, let's say you draw 100 tokens at a time instead of 20, the resulting bell curve of sample means becomes significantly narrower.
Oh,
The standard error of the mean decreases. Your sample averages cluster much more tightly and aggressively around the true population mean.
so we have this mathematical law that turns averages into bell curves. But how does this abstract token drawing exercise map onto a graduate student trying to measure human psychology? Like, why is the normal distribution ubiquitous in our specific field?
To understand the connection, you have to critically analyze what a psychological measure actually consists of. Let's return to the construct of general intelligence or cognitive ability. Do we believe that intelligence is a single, indivisible, isolated entity in the brain?
No. Decades of cognitive science tell us it's an amalgamation. It is a highly complex combination of working memory capacity, processing speed, spatial reasoning, verbal fluency, pattern recognition, and likely hundreds of other microvariables.
Exactly. When a participant completes a comprehensive cognitive assessment and receives a final score, that final number is not a raw single measurement. It is essentially an aggregation of their performance across all those underlying independent subskills.
Oh, wow. This is the aha moment. Because the final psychological score is an aggregation of many independent parts, the central limit theorem is already operating behind the scenes. Nature and our test design are doing the sampling and averaging for us.
That's it perfectly. Whenever a measurable variable is the sum or average of many independent random factors, which describes almost every complex psychological construct from extroversion to job satisfaction to depressive symptomatology, the central limit theorem practically guarantees that the distribution of those final aggregate scores across a population will approximate a normal curve.
It's not just psychometricians forcing the data into a shape. It's a fundamental reflection of how complex human traits are constructed from vast networks of minor influences.
It is a profound realization. However, as rigorous scientists, we cannot treat the CLT as a free pass to ignore our data's architecture. There are severe limitations, and misunderstanding them is how you end up with rejected manuscripts and irate peer reviewers.
Oh, for sure. Let's dive into those caveats, because this is where grad students often get obliterated by reviewer hashtag too. A common catastrophic mistake is assuming that just because you are doing psychology, your raw data is naturally normally distributed.
It's a huge pitfall.
Our source material issues a very stern warning about this, using the classic happiness questionnaire as an example.
Consider a standard survey utilizing a 7-point Likert scale, asking participants to rate their current level of happiness from 1 to 7.
Okay, so a researcher collects 1,000 responses. A terrifying number of students will immediately load that data into SPSS, assume normality, and run a parametric test like a standard ANOVA. But if you actually plot the raw responses, they might not look anything like a bell curve. The source points out the data could be completely flat. A uniform distribution where an equal number of people chose 1, 2, 3, 4, 5, 6, and 7.
Or it could be highly bimodal. Perhaps you surveyed students during midterms. The population might split cleanly into two camps. Those who are deeply distressed and answering 1s and 2s, and those who just finished their exams and are ecstatic answering 6s and 7s.
Leaving the middle of the scale a complete ghost town.
Right. The raw population distribution is a U-shape. The central limit theorem does not possess a magic wand that reaches into the real world and forces people's raw happiness levels into a bell curve.
This is the crux of the misunderstanding. The central limit theorem only applies to the sampling distribution of the means. If you take 50 random students, average their happiness scores to get a single number, and repeat that process 1,000 times, those 1,000 averages will form a beautiful bell curve.
But the raw data, the actual 1,000 individual human responses, remains fiercely bimodal. If you try to run parametric statistics that assume a normal distribution of residuals on that raw U-shaped data, your standard errors will be wrong, your p-values will be compromised, and you might confidently publish a completely spurious finding.
Which is the nightmare scenario.
It is, and this leads to another crucial issue we face in psychological measurement: method variance and response sets.
Oh, this is fascinating.
Sometimes the shape of your data has nothing to do with the psychological trait you think you are measuring, and everything to do with how participants interact with a piece of paper or a computer screen.
Right. Acquiescence bias is a massive one. Some participants will just agree with whatever statement you put in front of them, pushing your data into a skew. Or extreme responding, where certain individuals only use the 1s and 7s, creating artificial bimodality.
Yeah.
If your scale is highly susceptible to these biases, the averaging effect of the CLT might just be mathematically smoothing over fundamentally flawed data.
You might achieve a mathematically perfect normal distribution of scores, but you are reliably measuring their survey-taking habits, not their actual anxiety or extroversion. You have to interrogate the raw data before you blindly trust the theorems.
Always look at your raw data. But assuming we have rigorously designed our study, controlled for method variance, and we are working with robust, aggregated constructs that genuinely approximate normality, we unlock an analytical superpower.
We do.
We can utilize the properties of the normal distribution to solve one of the most frustrating problems in research, comparing metrics that operate on entirely different scales.
This is the operational payoff of everything we've discussed. We move from theory to application with z-scores and standardization.
Let's set up a scenario that every grad student running a meta-analysis has faced. You are trying to synthesize 40 different papers on adolescent stress. Lab A measured stress using a clinical interview that produces a score from 0 to 100. Lab B measured it using a custom behavioral task that measures cortisol reactivity in nanograms per deciliter. Lab C used a 20-item self-report survey that gives a score from 20 to 140.
You are staring at a spreadsheet filled with numbers that share absolutely no common baseline. You cannot simply average a score of 85 from Lab A with a score of 110 from Lab C.
Yeah.
The units are fundamentally incompatible.
Right. I like to conceptualize this as a currency problem, but we need to evolve the standard metaphor a bit. It's not just about converting yen into dollars so you can compare the numbers. If you just convert currencies, a billionaire in yen is still a billionaire in dollars.
Yeah.
But what if you want to know who's relatively wealthier within their own specific society? $1 million makes you quite wealthy in some nations, but perhaps just middle class in a hyperinflated economy.
To truly compare their standing, you don't look at their raw bank accounts. You measure how far their wealth deviates from the average citizen in their specific economy.
Exactly. Standardizing data into a z-score is exactly that process. It is a translation layer that strips away the arbitrary units of the original measurement, whether that unit is survey points, milliseconds, or nanograms of cortisol.
It re-expresses the raw score entirely in terms of its relative distance from the mean, using standard deviations as the universal ruler.
You convert everything into standard deviation units. A z-score tells you, unequivocally, exactly how many standard deviations a specific data point is situated above or below the mean of its own distribution.
The mathematical formula to achieve this translation is surprisingly simple, almost anticlimactic, given how powerful the result is.
It really is.
To find a z-score, you take the raw score, subtract the mean of the distribution, and then divide that result by the standard deviation. That is the entire engine. Raw score minus mean divided by standard deviation.
The logic of the formula is highly intuitive, too. By subtracting the mean from the raw score, you are recentering the entire distribution around 0. If a participant scores exactly the average, their raw score minus the mean is 0. Their z-score is 0. A z-score of 0 instantly communicates perfectly average.
And the second step, dividing by the standard deviation, rescales the spread. It converts the original messy units into clean, standardized increments of 1, 2, and 3.
Let's ground this with the concrete example from the source material. Imagine a custom-built psychological inventory designed to measure spatial reasoning. The normative sample establishes a mean score of 100 and a standard deviation of 25.
Okay, so a new participant completes the inventory and receives a raw score of 97. If we just look at the 97, it doesn't tell us much, so we standardize it.
Right.
First, we find the difference from the mean. 97 minus 100 equals -3. They scored 3 raw points below the average.
Now we translate those raw points into our universal currency by dividing by the standard deviation. -3 divided by 25 equals 0.12.
Their z-score is -0.12. Instantly, the ambiguity is gone. We know they performed just slightly below the average, sitting very close to the center of the bell curve.
What if another participant bombs the test and scores a 50? Raw score 50 minus the mean of 100 is -50. We divide that -50 by the standard deviation of 25, yielding a z-score of -2.
A z-score of -2. And because we spent all that time mapping the territory with the empirical rule, that -2 is incredibly rich with meaning.
Oh, absolutely.
We know that 95.4% of all scores fall between a z-score of -2 and +2. By scoring a -2, this participant is sitting on the extreme lower boundary of that vast middle majority.
Conversely, a raw score of 150 on this test yields a positive 50 difference. Divided by 25 gives a z-score of +2. They are sitting on the extreme upper boundary.
This arithmetic is straightforward, but the true analytical power, the reason standardizing is foundational for grad students, emerges when we execute the apples to oranges comparison.
Let's look at two completely different participants taking two completely different cognitive assessments.
Participant A completes the spatial reasoning inventory we just discussed, rate of 100, standard deviation of 25. They perform quite well and achieve a raw score of 125.
Okay, participant A gets 125. Participant B is in a different lab taking a classic standardized IQ test. Mean of 100, standard deviation of 15. They achieve a raw score of 150.
If you present those raw scores to a layperson, the conclusion is obvious. Participant A has a 125, participant B has a 115. Participant A clearly achieved the superior result. 125 is a larger magnitude than 115.
But as researchers, we know that comparing a 125 on a scale with a 25-point spread to a 115 on a scale with a 15-point spread is mathematically illiterate. We must translate them both into standard deviation units.
Let's standardize participant A's score first. Raw score 125 minus the mean of 100 leaves 25. We divide that by the test standard deviation of 25. 25 divided by 25 is 1. Their z-score is exactly plus 1.0.
Now we process participant B raw score 115, subtract the mean of 100, which leaves 15. We divide that by their specific test standard deviation, which is 15. 15 divided by 15 is 1. Their z-score is also exactly plus 1.0.
Despite the raw scores appearing significantly different, and despite the variance of the underlying tests being entirely different, the standardization reveals the deeper truth. Their z-scores are identical.
Relative to the normative populations of their respective assessments, they performed identically. They both demonstrated an ability level exactly one standard deviation above the mean. The z-score allows us to see past the superficial illusion of the raw numbers.
This mechanism is why z-scores are the invisible architecture holding up modern data analysis. When you read a journal article that utilizes a proprietary, unvalidated survey instrument, the raw mean and standard deviation are essentially meaningless to you.
Yeah, you have zero context.
Right. But if the authors report that a specific experimental group had an average z-score of plus 3.0,
your statistical intuition instantly triggers an alarm. The empirical rule dictates that a z-score of 3 is an extreme outlier, representing an event that occurs in only about 0.15% of a normal distribution's upper tail. You immediately comprehend the sheer magnitude of the finding, entirely independent of whatever bizarre scale the researchers invented.
And building on that, standardizing scores is the direct gateway to calculating effect sizes, which is what grad students are constantly battling to prove.
Yes, the elusive effect size.
When you calculate Cohen's d to show the difference between your control group and your treatment group, you are essentially calculating a standardized difference. You are asking how many standard deviations apart are the means of these two groups.
If your treatment moves the needle by half a standard deviation, that is a universal metric of impact that any researcher in the world can understand and incorporate into a meta-analysis.
It provides a shared, rigorous vocabulary for the entire scientific community. It allows us to synthesize fragments of data generated across decades and continents into a cohesive understanding of human behavior.
Let's synthesize the journey we have taken today. We began by abandoning the discrete, integer-bound world of probability and embracing the smooth, infinitely precise domain of the continuous normal curve.
We learn to navigate that continuous density, not by looking at single points, but by mapping the areas under the curve, heavily relying on the inflection points that define the 68-95-99.7 empirical rule.
We confronted the chaotic reality of raw behavioral data and discovered the central stabilizing mechanism of statistics, the central limit theorem, which explains how the aggregation of random variables inevitably draws the distribution of sample means into that familiar Gaussian bell shape.
And finally, we operationalized all of this theoretical architecture by utilizing z-scores, allowing us to strip away arbitrary units and translate any data point into a universal currency of standard deviations, making true cross-metric comparison possible.
It is an incredibly potent methodology. However, before we conclude, we must return to a critical, somewhat unsettling caveat that our source material introduces and that we touched upon earlier regarding method variance. It is a philosophical question about the nature of what we are actually standardizing.
We acknowledge that individuals often exhibit highly consistent test-taking styles. Some participants are inherently conservative, confining their responses to the neutral middle of any scale.
Right.
Others are consistently extreme, gravitating to the absolute poles of 1 and 7, regardless of the construct being measured.
If a participant's response is dictated more by their idiosyncratic interaction with a Likert scale than by their genuine internal state of extroversion or anxiety, then the raw data is essentially measuring their survey-taking personality.
The provocative question is this. When we take all of this potentially confounded survey data and we apply the central limit theorem to guarantee normal sampling distributions, and we meticulously calculate z-scores to perfectly standardize the results, are we actually revealing profound mathematical truths about the underlying architecture of human psychology?
Or are we merely utilizing brilliant mathematics to perfectly organize, map, and standardize our own methodological illusions? Are we deploying the full power of the Gaussian curve just to meticulously document how humans behave when handed a clipboard?
It is a vital vulnerability to consider. Mathematics can perfectly standardize data, but it cannot validate the fundamental truth of the construct being measured. A perfectly standardized illusion is still an illusion.
That is the burden of the researcher. You must ensure the integrity of the input before you trust the elegance of the output. So next time you are staring at a 75 on an output sheet, you possess the tools to look past the raw number, to standardize the data, and to uncover exactly where that performance truly sits in the landscape of probability. Keep interrogating your measures, keep standardizing your comparisons, and we will see you on the next Dupe Dive.